All right. Hello, everyone. This is a presentation slide deck on my literary survey on the subject of minimizing interconnect delays in VLSI design. So here are the 6 main papers that I choose to present today. The first one is about buffer insertion. The second one is a particle swarm optimization approach for routing. The third one is also a particle swarm optimization approach, but it's a big improvement on the first one. The fourth one is a wire optimization technique. The fifth one is a layer assignment in global routing under multi-tier interconnect structure, and this is to again minimize the interconnect delays. The sixth one is the layer assignment for VLSI interconnect delay minimization. The fifth and the sixth paper are different because they use different algorithms and different approach in how to assign layers and how to minimize the delay. So here's what I'm going to present today. The first section is going to be on the background on VLSI interconnects, its history and trends. The second section is going to be on the subject we're discussing today, which is improving interconnect delays with these 4 sort of subsection. First one is routing algorithm. Second one is buffer insertion. Third one is layer assignment, and fourth one is wire optimization. All right, so background. So the transistor has existed for quite a while now. The probably the first transistor is the one originated in 1947 by Brattain and Shockley. They call it the trans resistor, and later just mashed the two words together, and now it's a transistor. And then probably the biggest breakthrough is in 1950, where Shockley introduces the P and N junction transistor, and from there many improvement has been made in order to shrink the size of the transistor and to produce continually more complex circuits. And probably the biggest or the biggest breakthrough is the complementary MOS or CMOS technology, originated in 1963, and it is pretty much dominates the transistor market for a very long time, probably still until the 1990s or 2000s, or maybe even today. Many of the integrated circuits are still using CMOS with 45 nanometer technology, although the future of CMOS is being questioned because people are having a very hard time to scale down the CMOS device. Although some people say that they have done it in 10 nanometers, but there's still a lot of questions on, if physical laws are broken, or if the reliability of the device is still intact. So here are the example of the first transistor. The one on the left is from Texas Instrument, and the one on the right is from Fairchild Semiconductor. Yeah, the one on the left is very, very different from the one we have today. So talking about transistor, probably everybody is going to talk about Moore's law, and um, Gordon Moore is at the time working as the Director of Research and Development at Fairchild Semiconductor. And in the 35th anniversary of the paper, the magazine Electronics, he predicted that the number of transistors on existing microchips will double every 2 years. And his prediction is true until today, even though many people questioned his this prediction due to the fact that there are a lot of limitations, and there aren't great breakthrough that will completely remove these limitations when you are scaling the chip, which is, in a very small area, to the billions and tens of billions of transistors. Um, yeah. So pretty much, I think the scaling has slowed down. Maybe now it's not doubled anymore, not doubled every 2 years anymore. Maybe it's doubled every 3 years, but that's why we are looking into minimizing the interconnect delays, because it is a very important part in further scaling our microchips. So here is a graph of the delay trends. So as you can see, the smaller the transistor, the more advanced they are, the lower delay they have. But for around, I think, 20 years, the delay of the transistor has been pretty much optimized, and it hasn't decreased for a very long time. But however, the delay in the interconnect is increasing by a very large amount, because when we have a lot more devices, then a lot more interconnect has to be made, and then the network of interconnect becomes very complicated, and there are physical phenomenon with the inductance and with the resistance happening inside the circuit that would further delay the switching speed in the interconnects. And right now, as you can see, in like 16 nanometers, right, the interconnect delay is about 1,000 times the transistor delay. So here comes a section that we will talk about improving the interconnect delays with the 6 main papers that I show above. So the first problem we're going to talk about is routing, right? And of course, one way to improve the delay is to find the shortest path, right? But also obeying, setup and whole time criticality from a source to a sink. However, in VLSI design, since space is a commodity and the number of devices keeps growing and growing, routing a straight line from point A to point B, which is the least distance, is impossible, right? Therefore, in order to simplify routing algorithm. Routes are constrained to run only horizontally or vertically, which looks like Manhattan, pretty much. Hence, the total length is a lot longer, which raise a lot of needs for efficient routing algorithms. Um, so the routing problem is sometimes referred as, in computer science as the rectilinear Steiner minimum tree problem, or RSMT. Well, actually, the actual problem is that solving an RSMT is NP hard, or NP is non-polynomial, which means that there is no solution that gives an answer in a polynomial amount of time. AKA, it's pretty much impossible to find an exact solution in a reasonable amount of time. So what people have done over the years are developing lots and lots of approximation and heuristic algorithm. So here are some of the approximation algorithm. We have ACO, which is ant colony optimization. PSO, which is one we talk about today, is particle swarm optimization. DE is differential evolution. ABC is artificial bee colony, and FA is firefly algorithm. The great things about these algorithms is that they are almost all um, based on or inspired by nature. So um, it is easier to understand them. Also, the reason why we are only focusing on PSO is that if you look at this chart, PSO solves the most amount of routing problems. So here is PSO. So how PSO works? So the definition of PSO is that we have a swarm, a population of particles in a multidimensional space with only two characteristics, their velocity and position. They are all trying to roll towards the lowest or the minimum point on a multidimensional surface while keeping track of its best record and the best record of the entire swarm. All particles will try to roll towards the particle with the swarm's best record. Once enough particle rests on a location, which we call convergence, then the algorithm stops and report its optimal parameters. And in order for an algorithm to find, what is the best record, here we have the p-best and g-best. P-best is personal best, g-best is global best. We need to define a fitness value. And now here we see on the right there equation 1 and equation 2. Basically, equation 1 is how you would use to update the location. It is very simple. The location of the next time step is the current location plus the velocity. And the velocity is updated according to some sort of acceleration plus a configuration, a function of p-best and g-best. Okay, so now how do we formulate the VLSI routing as a PSO problem? We can see the swarm search space is equals to the routing VLSI area. The particle is or are the paths from the source to sink. The fitness function is the interconnect delay from source to sink, and the optimal path is the path with the minimum interconnect delay. And in main paper 2, Ayop et al., the authors use an Elmo delay model to calculate the total delay from source to sink. Pretty much um, most people use Elmo delay because it is simple to compute. So in their example, as you can see on the picture up top here, is that the path is uh, source to E1 to E2 to E3 and etc. to sink. As a more general case, if the number of dog legs is n, then the particles I, position, and velocity can be represented as a matrix um, in the picture below. And since the fitness function is the total delay from source to sink, the function above, the function p here, the total path length, sum up all the segments. Also, to minimize total delay, the author of main paper 2 suggested that every 6 segment a buffer is inserted at random. So there's a random chance that a buffer will be inserted. However, Anyop et al. Did not perform wire and buffer sizing, and many subsequent works expanded on their work. Main paper 3, for example, by Yusuf et al., introduces a two-step binary particle swarm optimization in which the particle position x is modeled as a binary sequence, x1, x2 to xq. The author looked at x1 to xq as binary bits in which the first BPSO optimized for the wire and buffer sizing. The first 3 bits represent the type of wire, fourth bit indicates the use of buffer, the last 3 bits represent the type of buffer. And then the BPSO number 2 find the shortest path and the best location of buffer insertion along the wire. However, since BPSO uses only binary, the exploration capability is low, which sometimes leads to low conversion rate. Hence, Khan et al. Introduced discrete PSO, but only choose certain bits from one iteration to another to mimic sort of genetic selectivity, which is a type of mutation which fixes the conversion problems, although would take more time. Also, Nath et al. Propose constricted PSO with mutation, which is similar to Khan, but achieve better delay with a slightly higher number of iterations. So here is the second method mentioned, which is buffer insertion. So in VLSI circuit, optimization using PSO or ACO or any of the genetic algorithm is often not enough because of the complex nature of VLSI designs. One such complexity is the inductance effect in the circuit. So here are the two effects, right? Since the wide wire is used in the upper metal layer, for example, in a clock distribution network in which high frequency is running through, then significant inductive effects can slow down performance, such as the skin effect and yeah. Also, since switching speed is regarded very highly nowadays, ignoring inductance can cause very large error in simple propagation delay models, such as the Elmo delay model. That PSO and other algorithms are mainly based to work on. Hence, the algorithm in main paper 1 will take a predefined path or tree and optimize the use of buffer insertion, aka the number of insertion and size, by applying what's called the cuckoo optimization algorithm, or COA. So COA is inspired by nature, again, the nature behavior of the bird species cuckoo. Cuckoo lays eggs in other bird species' nest. If the host bird recognizes the cuckoo's eggs, then some of them are destroyed. The rest have an opportunity to grow up. The goal of the cuckoo is to find the optimal habitat, which is the same as maximizing the number of surviving eggs during each generation. Hence, the optimal habitat will have the most amount of food resources and the most similarity between the host species' eggs and the cuckoo's eggs. To realize this behavior into an algorithm, then we first initialize a habitat matrix of size, population versus variable. The variable is a number of optimization variables. The profit function is basically a function of the habitat. And in order to turn this into minimization, then we say that the profit is a negative of the cost. Then we have to define the ELR, which is the egg laying radius for each of the cuckoos. Then dedicate some eggs to each of the cuckoos, and let the cuckoo lays egg randomly right inside their defined ELR. And then we kills the eggs recognized by the host birds. Let the surviving eggs hatch and grow. Evaluate the habitat of each new grown cuckoos. Limit the maximum number of cuckoos and kill those who lives in worse habitat, which we can use the profit function. And then let the living cuckoos migrate towards the best known habitat with some deviation. And we can see that at the end, they will definitely converge on a solution or on the optimal habitat. Um, so here, the author applies COA on an RLC line. And you can see the first picture, on the top here, there's a line, and there are many buffers that are triangle. Um, yep, and they're inserted in between in order to raise uh, the signal voltage to an appropriate level and to reduce the um, propagation delay. And you can see here uh, TPD total is a total propagation delay, which equals to K, or the number of segments, or basically the number of buffers, times the propagation delay from one segment to another. And then we use that as the cost function. And the COA can be applied to find the best size, since all buffer in a line will have the same size. And then the algorithm can be ran a number of times from, for example, 10 from k equals 1 to k equals 10 to find the best number of buffer. Then the author uses HSPICE to simulate and found that the lower the inductance, the better the reduction in total propagation delay. However, the algorithm showed better improvement as the length of the interconnect gets longer. In summary, the author saw about 20 to 30% improvement in comparison with an unbuffered line. And then also the author the authors apply COA on an RLC tree. So there are two types of tree, the balanced tree and the unbalanced tree. And using the same technique performed on the RLC line, the author presented that their algorithm provides about 50 to 65 reduction in propagation delay. So let's come to the third method, which is layer assignment. So if you can imagine circuit only scale in width and length, and then routing algorithms and buffer insertion algorithm would be enough to optimize the circuit. However, when there are billions of connections between millions and millions of devices, then scaling in 2D is impossible if you want to maintain the speed requirement. Hence, a 3D global routing under multi-tiered interconnect structure is needed for the integrated circuit to keep scaling. So you can imagine that some nets will be on layer 2, or some nets will be on layer 6, depend on their requirements and their relationship with each other. And we have to assign these nets to these layers in a fashion that would minimize the delay between them. So authors in main paper 6 look at the problem of 3D global routing as solving a maximum cut problem of an undirected graph. So you can imagine that give a graph where each node represent a different net or a cluster of nets. The weight between two nodes is the model delay between the two nets or cluster of nets, which is usually the number of vias needed to connect them. A cut in the graph will separate the nodes into two groups, A's and B, representing two different layers. Some nodes may be locked into a group due to design constraint and some sort of priori knowledge. Hence, the minimum delay can be achieved by maximizing the sum of the edge weights that connects the opposite groups plus the sum of the node weights in group B. However, the maximum cut problem is NP hard again. Hence, the author proposed a heuristic algorithm, which is a generalization of a graph bipartitioning algorithm produced by Kernighan and Lin. And the other paper, main paper 5, produced by Jian Cheng et al., looked at the layer assignment problem very differently. So in their algorithm, the 3D structure is actually transformed into 2D, where delays and via counts is minimized there. And then the projection is used to transform the 2D assignment back into 3D. And this algorithm that they propose is divided into two different stages. The first one is a layer assignment for simultaneous delay and via count minimization, and layer and two minimization of maximum delay. So in stage 1, which is short for SDLA, layer assignment for SDLA. Step 1 is the initial layer assignment. Step 2, they call it rip up and reassign. In each iteration, RA reassigns one layer assignment at a time for nets that have wire overflow. So the wires that without track. And then it iterates until the total wire overflow is below a defined threshold. Greedy improvement is step 3. It rips up, and this is where they would transform the 2D assignment back to 3D, and then reduce the delay and via count there. On each of the step, a single net layer assignment algorithm for SDLA is performed. So each of these steps, so this SDLA algorithms performed in each of the steps in order to assign nets to their best layer. So here's a figure of the SDLA algorithm. In essence, it treats the nets to be connected as nodes on a predefined graph, which corresponds to different metal layers. Then the algorithm iteratively travel through the entire graph using depth first search, calculating the delay model by the using the Elmore model, and then return the path in this defined graph with the best node configuration. And then here's the stage 2. minimization of maximum delay. Stage 2 is not that different from stage 1. However, the author argues that stage 1 focuses mainly on optimizing all the nets at once under the constraint of delay, via counts, and concession. But then it's since it focuses on optimizing all nets at once, it will miss a few things. And stage two is there to improve upon the result from stage 1 by looking at individual nets and their individual connection, and then try its best to reduce the number of via needed. And the author provided the result uh, of this two stages process in comparison with a state-of-the-art method, which is NVM, negotiation via count minimization, and found that their method outperformed NVM in terms of delays. They claim 80 and 90% better, but they have a very similar via count. So probably their via place in places which are a lot better, and the layers are assigned much better than the NVM algorithms. Also, the authors provided a graph of the relationship between the via count and the delay reduction, and this relationship is a function of the parameter lambda. And previously here, lambda is a relative importance of net delay versus via count, and it is looked as a trade-off. And you can read the reason why they think that is here. And they say that if lambda is around 0.15, as we can see it's around here, then it would be best because the delay hasn't going up. I think this is sort of exponentially. It's right before it goes up exponentially. All right. So the fourth and final method is wire optimization. So in main paper 4, Dami et al. Introduces a new perspective on how to reduce interconnect delay for 7 nanometer technology of today's age. Other papers presented before were mainly focused on much larger technology, so 45 or 180. The authors believe that in this technology, traditional buffering and upsizing techniques are no longer effective due to area and power constraint. Also, devices are way too optimized to have further impact on delay. Hence, the author argues that designers should take advantage of the rerouting transform for setup and hold in existing EDA tools. Then the author took notes of the wide range of resistivity in metal layers. You can see in this table below, metal 0 and 1 mostly used by standard cells, which we will exclude. Router usually use metal 2, so router a software algorithm in EDA. However, changing from metal 2 to metal 4 reduces resistance by 54% because the wires are bigger. So the resistance is much less. More space for electron move. Changing from metal 3 to metal 4 reduces resistance by 46%. Hence, the author took this insight and applied a guidance to the EDA software such that critical nets will only be routed using up to layer 4, and all other nets with less criticality will be routed with all layers. To limit any side effect to quality and timing, the router is driven using non-default rules. So the essence of this is that critical nets will only be used to layer 4 so that there will be other layers for other nets, because other nets are often uh, is a lot more numerous than critical nets. And here we can see the author tested their theory using this Nitro SOC tools. They offer a set of TCL script that include the commands, and then they apply these commands right after the post clock tree synthesis. And this is the design flow of the process. The small insight, however, offer great result as the net delay is globally reduced by 50%. The author also tested their method against 6 different designs, finding that the worst negative slack and um, the TNS were improved up to 13% and 56% respectively. Here's table 1, table 2, and table 3, and here are my references. All right, thank you very much for listening, and have a wonderful day.